Welcome back. In the case of generalized linear models, here is the idea. Now, in the naive linear model, we assume that the h theta or the hypothesis function is a linear combination of different dimensions of the data, right, or the input features as they are called. Now, why should they be a linear combination of them? They can be quadratic combination of them, right. For instance, you take the first dimension of data, squared it, take the second dimension of data, cube it, right, and then take a linear combination of all of those dimensions, right. Now, can't this sort of a model be learned using the ERM is the question. Of course, you can do it where your h theta, so your h theta of x in the linear case, in the naive linear case, h theta of x is theta 1 times the first dimension, theta 2 times x2 and so on, and we had theta d times xd, where xj is the jth dimension of the data. Okay, instead of linear combinations, one can consider non-linear combinations as well and linearize them. Non-linear combinations of data dimensions. So, what does this mean? You have h theta. Now, h theta of x is equal to, so theta 1 times the first dimension. Oh my god, I've used superscript for this thing already, right? Um, yeah, that's what I was thinking. It looks a little complicated, no? So this is, let's say, cube plus theta 2 times the second dimension rise to 4. See, it looks like x squared to the power of 4. Please note that superscript is for the dimension and whatever comes outside the parenthesis is the power, right, and so on. So this can be one way to model it. Now the question is, how do you do ERM with this sort of a framework? So these models are called generalized linear models, where the above case can be represented via pre-computed kernels. Let's say pre-computed transformations. So what are these is that, so given x, okay, define x cap that's equal to some phi times x, where phi is a fixed transformation or kernel. So let's call this transformation. So what do I mean by this? Let's say that I have x, x cap can be the first dimension of x raised to 2 plus the second dimension of that raised to 3, or yeah, not plus, sorry. So this is, and the third dimension of this can be, let's say, the first dimension square plus the second dimension to the power of 6 and so on. You understand? So where phi of x, you do it dimension wise, where you take the first dimension and you make it undergo some transformation. See phi 1 of the first dimension, and you have phi 2 of the second dimension and so on. So you have, see, how many transformations can we learn on data dimensions? That's a design choice. Okay, you can do it whatever, right. So this, in fact, these transformations need not be function of only one dimension, this can be function of multiple dimensions of data as well. You see what I'm saying? So for instance, no, this, the third dimension of this particular example in the transformation is a function of the first and the second dimension. You see what I'm saying, right? So this is some function of the data dimensions. So I'll just write it as data dimensions, so just to make it general. Now what did we do? This function phi, okay, is taking the data x and mapping it into some other space x cap. Now this x is in Rd, okay, and this can be in some Rp, and phi, the function phi, right, is a design choice, user defined design choice. Do you see what I'm saying? Let's say that you are given data d, okay. I define transformations on the dimensions of data using a pre-computed fixed function phi, okay, and transform my data from d dimensions to some other p dimensions. So this phi, the function that is transforming from d to p, is something that I choose. I meaning user would choose. Now suppose you are given data x, okay, in let's say 2 dimensions, okay, or let's say 1 dimension. Now what I will do is I will define another x cap as 1 x squared, right. Then and then do ERM using the linearity of models, then whatever was the linear model now becomes a quadratic model. But you are still doing solving linear regression because you have transformed the data and the model is now linear in the phi space, not in the x space, linear in x cap space. That is why the name generalized linear model. I will take questions in a while. So you define this and then subsequently solve ERM with a linear model, with a model linear in phi x space. What happens is, given D, okay, compute, so transformed data first, let us call it D cap, which is equal to now phi of x comma yi. Note that the underlying distribution would change in this case, because what we are doing from a probabilistic standpoint is that we are transforming the random variable from one space to the other, which means the distribution would change, but we do not care here because we are solving ERM, right. So this is now phi of xi is now in Rp and y does not change, it is still in R, okay. And then what you do is find theta is already taken, no, theta cap star as argmin over theta cap 1 by n. This is now phi of xi transpose theta cap, writing it as theta transpose x, no. So we will write it as theta cap transpose phi of xi minus yi. You solve this problem and now this will be equal to where this phi matrix is, now instead of stacking x as columns, now you stack This is the dth dimension. See, as I said, no, I'm actually overloading the notation a little. This all these dimensions of phi need not be functions of one dimension of data. It can be functions of multiple dimensions of data as well, right? So let's look at an example and then I'll stop for questions. Example is, suppose x is in R and y is in R. Okay. Now suppose I define my phi of x as 1 x squared, right? Then ERM with theta transpose phi x, okay, is same as ERM with a1x a2x squared plus 1. That is it. Okay. So now what was quadratic in your data space became linear in the transform space. So that is why so this is called polynomial regression, by the way. So you are regressing using polynomial functions. Now polynomial regression is always a generalized linear regression with a fixed polynomial kernel, that is it. And you can extend this idea to anything, it need not be restricted to polynomial functions, right. These phi can be, let us say, sine functions, they can be exponential functions, or it can be sinusoidal functions or anything. The idea is that you are given x, transform it into some other space using fixed transformation and then solve linear regression there. In fact, I'll ask you a question here. You know something that you do, I mean, you know something that already is in this framework, just that maybe you do not recognize the name. Do you know about Fourier series? They are exactly this, where your phis are sines and cosines. So representing your data as a linear combinations of sines and cosines. This is exactly what it is, right. Fourier series is ERM that way, right. So you take your phi to be linear functions of data with fixed kernels. These are called kernels, transformations, and then you find out the coefficients of the linear coefficient using the least squares methods. So that is why this is called generalized linear regression or generalized linear models, where given data you transform your data into some other space and then assume your model to be a linear combination of those dimensions. But note that assuming that data is the dependent variable y is a linear function, linear combination of dimensions in the kernelized space or transform space, does not mean that it is linear in data space. In fact, it is the other way around. I mean, if you have transformed the data using a nonlinear function, it is almost always that the y is not a linear combination of data dimensions. It is a linear combination of the dimensions in the transformed space, unless your transformation is also linear. Suppose your transformation is also linear, then composition of linear functions is another linear function always, right. So that is why it becomes linear, otherwise it's a nonlinear combination. That is why these are called generalized linear models. So polynomial regression now also is a linear regression under a polynomial transformation kernel. That is it. Make sense? Okay. So yeah, I'll take questions now here. Where? Here. No. Okay. See, how many kernels we do use is a design choice. See, phi is a function of the original data dimensions. See, it need not be a function of x1, I am saying it can be a function of x1, x2, x3. The first dimension. Oh, these are the data, okay, data points. So now you are saying there should be n of them, correct? Yeah, it's a mistake. These should be, yeah. See, if I write this means that all of these phis are, say, okay, let me do it this way. I think a better way to write it is, there are n of them. So for every data point there is a transformation, and there are n data points, and therefore there are n transformations. Notations, so the underlying function is the same. This is okay. Okay, so you take the first data point, whatever is the transformation, you make it undergo that transformation, and you get the first transform data point, and there are n of them. But remember that this phi function, the dimensions of this phi function, right, or the phi vector post transformation need not be there need not be a correspondence, right. It can be the first dimension can be a function of first 3 dimensions of data, the second dimension can be a function of last 4 dimensions of data. This is completely user defined, this is a design choice. Come again? Yeah, that's again you choose that p. The question is, are there guidelines to design this transformation? People like Fourier, that was their life contribution. So they found out that if your input function is periodic, then you can use exponents, sines and cosines to represent that, right, so that the error is minimized. Now in the pre deep learning era, okay, lot of scientists, they dedicated their life to find this phi. So including my PhD thesis, during my PhD I was designing this phi for the problem of speech analysis. So what is the best data transformation? By the way, this is also called as feature engineering or feature learning. Given data, learn some features on your data, right, such that the okay, I'll ask you one other question here now that we are talking, right. One can establish equivalence between learning a particular feature and making the underlying distribution function more and more complex. What do I mean by that? Okay, I'll make a statement, you take it as a homework and do it. It's an interesting homework to do. Let's say that you build a base classifier, okay, by making an assumption that the class conditional densities for both the classes are Gaussian. You understand what I'm saying? You are building a base classifier by assuming that the class conditional densities are both Gaussian. You assume that they have the same variance but different means. See what happens to the base classifier. The answer is the base classifier will be a linear function of data. You will see that HB of x will be some linear function of data. So now if you make an assumption that your class conditional densities are Gaussians with the same mean with different variances, then base classifier will become a linear regressor. Come again? No. If you make the assumption that the variances are the same. No, I'm saying variances are the same, means are different, then it become linear functions of data. That's what I'm saying. It will become linear regression, right? So now from the ERM standpoint, let's say that I am assuming that I'm trying to model my my data using linear regression. Then I'm implicitly making an assumption that the underlying distributions of both the classes are Gaussian with different mean with same variance. That's the equivalence. Now suppose I make an assumption, I let go of that assumption that the variances are the same of the underlying class conditional densities. Then what happens? You can actually visualize that mathematically, right? Because we are in the base classifier, we are deciding based on the ratios of P of y given x for y equal to 0 and y equal to 1. So it will have the ratios of two Gaussian densities, and both of them are quadratic in x. Now if I assume them to be having same variances, the quadratic term will get cancelled away and only the linear term will survive. That's why it becomes a linear function of data. Now if I don't assume the variances to be the same, then the base classifier will become a quadratic function of data. You see, so only if you assume that only if you try to fit a quadratic regression model. Okay, if you use a quadratic regression model for classification, rather quadratic model for classification, you are implicitly making an assumption that your class conditional densities are Gaussians with different means and different variances. So, a generalized linear regression with a quadratic kernel or quadratic transformation is equivalent to building a base classifier with the assumption that the class conditional densities are both Gaussian. Exactly. Now to your question, so now what happens is that the moment we make a choice for phi, we are making a choice for the underlying distribution function, right. Now what happens if we assume that the class conditional densities are GMMs? What sort of a kernel should you have to choose? So we know that choosing a unimodal Gaussian is a bad choice, right. Suppose we make an assumption that the underlying density functions are GMMs. How does that translate to in ERM is the question. In those cases what we do is we will not choose this phi, we let the ERM choose the phi for itself. That is what a neural network is. Now so many decades people were doing feature engineering and trying to, so never in the history people never gave raw data as an input to classifiers. For instance during my PhD, right, I mean people used to laugh. So you record speech signal, right, or you look at a signal or you take an image, you do not give an image as an input to a classifier. What you do is you extract some features from that image by doing some fixed engineering. You know, for instance, if any one of you is doing an image processing course, you know, right, there are these shift kind of transformations and all these, right. What are those? They are actually these fees, extracting features from data and then use those in a classifier. Now what has happened is it was realized empirically that you do not have to do feature engineering, just throw raw data. I still remember my advisor used to laugh when just when I was finishing PhD, neural networks started making a lot of strides, and he was laughing. People throw raw data to these classifiers. How can they do it? So today nobody does any feature engineering anymore, right? So you take raw data and give it as input. Even NLP for that matter. If you are taking NLP course, there used to be bag of words, right? The other kinds of frequency estimates, and you give that as features. This is your fee. If you represent your let's say your data is a sentence, each token you represent that as one hot representation, and if you just take counts of all of them, counts of nouns and all that, they are actually some transformation of data that you use as input to your classifiers. Come neural networks, they said why even bother to learn phi? See, I still remember my advisor who is a very old man now. He used to stick the pictures of spectrograms of different speech sounds in his office. Just stare them, right. So stare at them, because looking at that you come up with some sort of a pattern so that you design a nice fee. People have named these fee after them. So there is Geber filter, right, and there are Fourier transforms, and there are wavelets named out of people, right. All of these are fees, fixed transformations of data so that learning becomes easy. Now come neural networks, they said don't try to fix, or rather use your, that's why first day I told you this is all ignorance modeling, right. You do not know how to design a nice transformation so that data becomes easily separable. You make your model itself learn what this fee is. We will see that, we will see ways of transforming data from one dimension to the other via ERM framework, which is nothing but the neural networks. We'll get to that in a while. So for now we are still in the age of Gebers and Fouriers and so on, where we transform the data from one dimension to the other and then we use ERM to solve it. No, there is no, that is a choice. The question is there any relationship between D and P? No. Okay. Uh, okay, has anyone of you studied wavelet transforms? I do not know if it is even taught these days. You have, right. See, there, right, in uh, you have this idea of how many dilations that you have to choose. That is your P. How many dimensions of your data you should choose for transformation, right. So how many features you will have to extract. If given an image, you can extract multiple features of it, right. That is your P. That is again a design choice. Okay. So this is about generalized linear models. Let us get to classification. We will stop here and continue in the next lecture.